No, you need to switch on your.
Okay, so hello everyone. If anyone from CMS, by the way, wants to join us, we are in Gatehouse and we are in seminar room 2 today, not in seminar room 1 because there is the algebra workshop in the other building. Anyway, let's start. So today's speaker is Malena, and she will talk about solving inverse problems with deep neural networks, robustness included. And yeah, I think the topic of today is deep learning with meets inverse problems. Okay, so Malena, the floor is yours.
Okay, can you hear me? Is that fine? Does it work? Well, hopefully, if someone's online, they can hear me. Oh, this is someone.
Okay, Martin.
Okay, cool, perfect. Great, thank you. So yes, I'm going to be talking about this paper, as Tatiana just said. It was actually suggested by the organizer of this reading group, and I think it's actually a really good paper to be presenting here because it presents a lot of numerical examples and it gives a lot of like empirical evidence of some claims they do, and I will like start talking about these things a bit more in detail soon. But I think it's really nice because it opens a lot of questions, which I think is nice, and hopefully I would like this to be a bit more of a debate. So I've opened some questions, I've shared my ideas and my perspective on them, but it'd be nice to hear what other people has to say too. So let's start just by talking about the abstract of this paper. Basically, they just claim that they want to do an empirical study of the robustness of neural networks when solving inverse problems. And they claim that they can really prove that neural networks can show or have the ability to show robustness or stability against different kinds of noise. So just to set the notation, we're talking here about very general linear ill-pulse inverse problems. They are interested in the undetermined case, so there isn't a unique solution of the problem. And basically they're thinking about things like medical imaging, where the measurement might be expensive or bad for some reason, like for the patient. So you're trying to have less measurements. Of course, you have an undetermined problem. And one of the nice conditions they have is that they don't assume a lot about the noise, but they think that the noise is somehow, well, has a noise level, which is smaller than some threshold. And a lot of the analysis they do will be based on kind of this key concept here that we do have a noise. We don't know exactly how it is, but it's norm, it's bounded by some level. And of course, they compare to some classical results. So they it seems that they really like this result in compressed sensing, which they don't go, they don't talk about it in detail at all. So of course, when they prove this in the compressed sensing scenario, they just give a quite long list or like a strong list of like some assumptions that you can do in your problem. But they can recover this really nice error bound when you have, so this is just like some reconstruction over some measurements, why? So they see that the difference between the exact solution and the reconstruction for the given measurements is bounded by some constant and then the noise level. And their idea is that if this is true and it holds, then you can empirically find this constant or just like show that that this can hold for different noise levels. And you could like, you know, you could imagine having some nice error plots, but you can see the linear dependency on this noise level. And I think the concept and the reason why they bring this up here is because they want to prove that in some cases some neural networks with some or a lot of particular choices on like architecture and training and a bunch of other tricks that I will explain later and they're in detail on the paper, then you can recover this kind of bounds for the errors. And again, I guess like talking about robustness in when we talk about neural networks is usually like people usually think about classification examples like things are not robust because we have adversarial attacks and small differences in my input or in my measurements can lead to very strong difference classification or like big errors on your output. And that's the way they think about robustness in the sense of like neural networks. So you can see like here, the kind of like trying to use this idea that I particularly have, that neural networks can be very unstable sometimes, because they say, well, in some cases, like in classifier maps, we're trying to map some big space into a low dimensional space with some discrete output, and the result, you get like, and as a result, you get like a vulnerable decision boundary. So it is easy in a classification task, or traditionally it's been proved that in a lot of cases in classification tasks, you can have specific attacks that mess up your solutions. On the other hand, they say that actually inverse problems are a very different kind of setting. So when we're trying to learn a reconstruction, or we're building an algorithm that will find a reconstruction for our problems, then we have some sort of regression task. And now the measurements are mapped to high dimensional manifold, like medical imaging or any other kind of like big solution space. And that should not result in something like a vulnerable decision boundary. Moreover, they claim that robust and accurate algorithms exist for many inverse problems. And I think here you can already see a key point in this paper, which is that they really use the word robustness or robustness with respect to noise in this idea, in this like neural network sense, where you think that a small perturbation in your measurements will lead up to something, potentially completely different, and we have no idea where it comes from. Whereas they claim that the lack of robustness in inverse problems is kind of solved. And I think personally here, I would just like maybe add some little comments, because it is true that we do have a lot of reconstruction algorithms, but I wouldn't say that, we are really robust and accurate for, most inverse problems. I think that's still a very challenging task. And the reason why inverse problems are not robust against noise is for like a very different reason, which is basically the whole conditioning and the whole nature of our forward problem, which is something they don't talk about much in the paper, as I will, as you will see as this unfolds. So the main contributions and findings that they proposed, basically, they just want to, again, test this robustness against statistical noise and also adversarial noise. And they want to study something that they call the performance gap. So they want to see in the specific setting of inverse problems, and using specific choices of neural networks and training routines, is it true that there is a big difference between having statistical noise in our measurements or really performing some sort of adversarial attack in the measurements? And then they show in subplots what is the qualitative and quantitative difference between those two kinds of noises in the inverse problem setting. Another thing that they do is, like, throughout the whole paper, they just use total variation minimization as a benchmark. So basically, they just want to see if there exists a neural network that they can find that is at least as robust as TV is for specific inverse problems. Another point of the paper is that they compare this idea of having noiseless training. So the idea that we usually train our networks with noiseless data. And they say that this is some sort of inverse crime. So they try to recover words and things that are used traditionally in the inverse problem community. And again, when we get there, also, I think this raises some questions about, how can we link together all the names that are usually used in in the inverse problem community and machine learning community, like, are those things equivalent? Are those things similar? Can we borrow techniques from one place to the other? Last thing that they kind of mentioned this here, but then you cannot see it that much from my perspective in the experiments, is that they say that the performance of the reconstructions is affected by the architecture, which is reasonable. But they don't dwell very much on why or how or in which way. And again, their central conclusion, and I'm just like quoting here, they say basically that the existence of adversarial examples in classification tasks does not naturally carry over to NN-based solvers for inverse problems. So basically that when you have an inverse problem, it's not that you can find a specific adversarial tag that will like blow things up in a completely different way. And they also claim that this kind of reconstructions can be like way better than classical methods or like state-of-the-art methods. And they are at least as robust. And again, they just compare with total variation regularization. So again, this paper is mainly focused on examples. And they use 3 different neural networks to compare in different scenarios. So they basically consider like end-to-end algorithms. So they usually, they just consider that you have the measurements and you in some way push them through the network and you get an outcome, which should be your expected solution, an approximation of the solution of your inverse problem. They use something called UNet. So basically, this involves a first linear inversion or some approximation of the inversion. So you have this like a double dagger. I don't know what's the name of the symbol, whatever, this double dagger, which is something like, a pseudo inverse, an approximation of the inverse, solution of a Tikhonov problem. It can be anything really, just something that we know that approximately inverts the inverse problem in a way that, and I think here there's another one of those tricks. We need that when we first apply this, the result has not blown up already. So we assume that, like implicitly, I think they're assuming that there is some sort of regularization in this a double dagger, or that our neural net and our inverse problem is not too badly conditioned. And then we just use a neural network to basically clean up this data and just like produce something that's really better. So this will be the UNet, that's the U, so it's a UNet in this network here. So the first post-processing network just consists of using first this a double dagger and then a UNet, and then you get your output. The second method they considered is this theta FL, which is a fully learned network, which is just something called tiramisu, which I think it's quite a cool name, but I hadn't heard of before. So the difference between this fully learned network and the post-processing network, of course, is the linear inversion. Like in this case, because we want to fully learn it, we learn some operator, some linear operator L, which mimics this pseudo inverse or in some way. And it's also learned in the training. And then instead of using a UNet, we use this tiramisu-net. And I don't understand why exactly. The only thing I know, it's like some sort of refinement of this UNet. So it's based on like what's the name of that? When you have like a lot of like a skipped connection in each layer. Well, whatever. It's like some sort of Well, yeah, I can't remember the name of the network that has some sort of like skip connection, but at each, really in each layer. ResNet, yeah, thanks. So yeah, it's like some sort of ResNet. And lastly, they also compare with iterative networks, which basically, again, have a first linear inversion, and then they just keep going back and forth with some UNet, which kind of cleans up a bit the mess, like very like loosely speaking, and some data consistency term, which basically does some sort of like gradient step on the feature data term. And of course, it depends on the operator and the measurements and some other parameters. Okay, so again, they claim that these are like just very general. I think you will all agree with this. There's no very fancy specific tricks. They're just really trying to see, is there some baseline neural network that we can use without having to assume too many things. The way they train it, again, doesn't have a lot of tricks. They just use data pairs. I think it's worth noticing that they use something called jittering, which basically consists on artificially adding noise, usually at different noise levels. And they claim, and it kind of makes sense, that if you train with different noises, then you'll be robust to noise changes. So yeah, again, this jittering is just like artificially adding some noise with some distribution to your data pairs to increase the robustness. And I think for training they always use Gaussian noise. Then when they compare against other kind of noise, they will use other things. So I'll show it later. They use like either statistical noise, which is mostly Gaussian noise, but there's also some other cases. But the other cases are in the very long, what's the name, like annex, like the appendix of the paper. But I think for training is mainly Gaussian. And again, that's where I'm having a bit of a problem again, because you're saying that you think neural networks are robust against noise, but then you're still doing this like kind of data imitation trick in which you're training for different noise levels and different kinds of noise. So I don't know, I just feel it's not just the neural networks being or not being unstable or stable, it's that you're also adding some of the tricks to it to make it more stable to different noise levels. And again, I think that's one of the things that'll be interesting to talk about later. What is the stability of these neural networks that comes from the network, from the training, from like where is the stability coming from? And I think that's something interesting to discuss at some point. Anyway, they train using these data pairs, and what they solve is basically a minimization where they have like some given loss, which I kind of remember, I'm pretty sure this one was some like L2 loss was like pretty standard. They're like really trying to be as standard as possible. Where you have the output of your network, and you just compare it against the actual solution. So everything's supervised learning in this case. And then you have some regularization in the weights. And they use mini-batch stochastic descent and ADAM optimizer. So nothing too fancy. Again, they also briefly introduce what TV minimization is, just to be able to compare between both scenarios. And they really use TV minimization as some sort of like this state of the art of traditional solvers for inverse problems. And if you're not familiar with this, TV minimization basically finds the solution of your inverse problem, which is close to your so which would have some measurements that are close to your actual measurements, but also that minimizes the one norm of the discrete derivative operator of x. So mainly you're trying to find solutions that are gradient sparse. So if you were thinking about 1D signal, that would be something that's like kind of looks like this, has like kind of like some of that, like it's like a staircase, or has like sharp edges. And similarly in 2D, you basically has this like piecewise constant images. And what is nice about this TV is that like it's been out for quite a while now, so like with some conditions, and again, this is a very empirical paper, so it doesn't go into the details at all, but under some conditions, this has some provable robustness and has some computable error bounds under some noise levels. And last thing that they introduce as an ingredient for their examples is this idea of adversarial noise, which you'll be familiar with if you have looked at it in some other contexts. Usually this is used in things like classification, and it's like very famous, like when you get this like very specific noise that makes a classifier, I don't know, like a panda instead of something else, like a chair, just by adding some very specific noise, which you've carefully chosen to be able to trick your network. So I think the idea here is saying, can we carefully pick up some noise that will trick our solver to solve this inverse problem? So the way they define this adversarial noise, they just want to find an additive noise to your measurements such that really tries to maximize the error between the reconstruction and your given solution. And of course, if we didn't have any constraints on this, we can just say like, oh, what's the maximal error that, also what's the maximum of this? You could just like, you know, make the error as big as you want, and then you like probably like screw up things. So you do still have to have some control over the noise level of this error. And they again use this using some standard solvers. So they just use some projected gradient descent and with Adam optimizer. This is not convex. So, you know, we don't know if there's a solution. We don't know how the solution looks like. Sorry, like there isn't one specific solution. And we don't know how the solution look like. So the way they account for this is just basically they run this several times and they just take the worst case scenario. So again, those are just mainly like small tricks to find a noise that gives you a bad reconstruction, and they try to find it with some like with limited computational time. So they just like, it looks really like they like run this like several times and they just like really just like pick the one that like looks the worst. And the way they will measure like all these experiments is like looking at the noise to error curve. So they just check at the relative noise level in contrast with the relative reconstruction error. So again, if you think about the linear bounds that we had for this like compressed sensing case, for this TV case, it looks, for the way they're presenting the paper, and again, that's just my perspective, but it looks like what they want to do is really to try to see if there is some sort of like linear dependency between the noise level and then the reconstruction error, how that looks like in different neural network scenarios, and even how that looks like for TV. And then they also plot some individual reconstruction results, which are always fun because then you can see like, oh, how do things fail? And maybe try to understand why it fails. And I think that it's not fully answered in the paper. I'm not sure if it's a question that we'll ever be able to fully answer, but I think it's quite cool to just spend some time thinking about it. And the two kinds of noise that they will use are statistical noise, and on the main results of the paper is all Gaussian noise, and this adversarial noise defined as I explained before. And the way the kind of like whole idea of this paper is set is that they trust TV. So they say, okay, TV is the state-of-the-art method that we're going to compare against. So that's kind of our gold standard. So we're going to use adversarial noise with TV. So like the words one explicitly for the TV reconstruction. And we're going to try to increase that as much as we can. And when the noise level is big enough that the TV reconstructs something that is really bad in some way that we just consider is not good enough anymore, then we stop. And then we're going to compare the performance of a neural network with specific adversarial noise for the neural network, but with the noise level that the TV was able to handle. So really here, like TV is kind of like taking the lead, right? It's like, this is how well we can solve it. And we're going to compare for the things that we know how to solve in a classical setting, according to TV is a good comparison. And then we're going to compare exactly those things in the neural network case. And again, they will compare with these three different kinds of networks, and they will use more or less some tricks to try to make these things converge to sensible things. So I'll show you the case studies. First case study, compressed sensing with Gaussian measurements. let's start with something really simple. Let's think about a 1D signal. We want to reconstruct this, I don't know, like line that appears in different colors. And then each of the horizontal lines of this plot corresponds to a different solver. So again, we'll start always with TV, which is the one that will lead the kind of experiments that we'll do. And then we start with a noiseless version of the data. And then of course we can reconstruct exactly the signal. And again, you know, we are using a really nice case scenario where this, like TV, is really perfect for this setting where we really have a piecewise constant signal. And then we keep increasing, yeah.
In this case, do we solve minimize TV subject to some noise?
Yeah.
So if the noise is 0, then the minimize TV subject will be equal to something.
What? So this would be.
Yeah. And then if eta is 0,
yeah,
then we basically minimize whatever you like over something that's also 8.
Well, the thing is like, so the thing is, because this is an undetermined problem, there's a lot of solutions. So you just take the solution that has smaller TV norm, given that it fully satisfies this. It is true that it has to fully satisfy this. And again, like one of the claims as well, especially when they start talking about inverse crime later, one of the things I would say about these examples that like there's a lot of nice things about these tests. So they do know there is a solution that is compatible and exists, and you know they know which one it is. And I think here the case is just like, let's try with things that we know how to solve and we know how they behave, and let's try to get back to the extreme where it starts being like weird. But there's nothing like tricky about this problem as a problem somehow, especially in the noiseless scenario. So again, they start with TV and then they like start increasing the relative noise. And all this noise here is adversarial noise. So again, like if you keep adding adversarial noise to TV up to a point, like it really doesn't do much, then you start seeing some like quirky things happening. You kind of like mainly lose contrast here, which kind of makes sense as well, because TV is always going to reconstruct something which is piecewise content. So it's quite nice to think, you know, what's the kind of tricks that we can do to make this not work. So I really think that you can spot here that it looks like the adversarial noise is just really trying to mess up a bit with the contrast of the image in some way, because the jumps are still very well found. And again, we're just penalizing a lot of jumps. So I think it is quite consistent with here. Anyway, they keep on increasing the adversarial noise until they decide that, you know, 15% is too much of an error. This looks very very, very different from the original signal. So that's as far as we can go with our traditional setting. And then they try to compare with the same amount of adversarial noise applied to all the different kind of networks. So they start with UNet, which this specific UNet just has some sort of like pseudo inverse at the beginning, and then they try to kind of like clean up the image afterwards with the UNet. And again, for a small adversarial noise with a small norm, like nothing seems to happen until, and I think this is quite interesting, and I think this should be very relevant, you get to the same not relative noise level than the TV case, and you obtain this, right? And if you look at the relative error, like it's smaller than the one that you had for TV case. But if I ask you if this reconstruction is better than this one, well, I'm not sure. So another thing that I think it's quite relevant is that all the comparisons in this paper are looking at norm in some very like Euclidean ways, like L2 norm between the difference. And I think it's also quite interesting to see which kind of effects does this adversarial training has on the different kind of reconstructions. And I want to point out that TV is based on properties that we know of the solution. So regardless of the noise, the kind of like properties that will be enforced in the solution are similar. So that's why I think that, you know, you still get something that is not quite as good, but because we're enforcing some properties that we know the signal has, at least that is conserved. So we get something that is sensible in this case. Whereas for something like this case, we're getting a much better reconstruction. It's like doing a better job in some places, but then when it fails, it's actually failing pretty badly. I mean, this thing here, it's like really an artifact. Like this in an image could look like a tumor. Like it's something that I would be quite careful to say, even if the error is quite small, I would be careful to say that this is a good reconstruction. Again, it's network dependent, so it depends on the architecture. Like if we look at other things, so like this one is learning the whole process. So this one is also learning kind of like the initial inverse or pseudo inverse of the linear problem. So we can see this one in this particular scenario has like much better results. And the unrolled iterative scheme has even better results, which kind of makes sense as well, because we're really enforcing data consistency throughout the network. And how do I say? Well, yeah, I mean, it's kind of reasonable that because this data consistency is incorporated throughout iterations, to me, it seemed reasonable that it performs quite well in this case, where we know that being close to, I mean, in this particular case, having a small relative residual is probably not too bad, because this doesn't seem incredibly ill-conditioned as an inverse problem. But again, those are the results they present. They show some other plots, and again, like the reason why I think they're so interested in this kind of plot that I will explain now is because they're really thinking, or they're really trying to see if there is some sort of error bound that is linear with the noise level. So here you can see the relative error of the reconstruction against the relative noise level. And this is for adversarial noise. And this is for statistical noise, which in this case is Gaussian. The one in the top is just an example. So it's the example that you saw earlier in the previous slide. So these are the specific errors for that specific example. And this is just an average version of it throughout the test set. They just take 50 examples and they average it. I'm not 100% sure of why they use this as a good measure. But again, if someone has any good idea what they use that of, if it makes sense to use something else, please say. And you can see that for TV, you have like a quite consistent linear dependency, both for the adversarial and the Gaussian noise. And the kind of more or less same thing happens with the different neural networks. And again, we're just measuring things in L2 norm. So that tells us something about this bound. But I think it's a good question to wonder if that's the right thing to do. Yep.
It's actually, if you think about TV, then the linear dependence of it is actually in the fragment distance, not in the L2.
Yeah, that's true.
So maybe it just happens.
That's true. But also, I'm trying to think, does that, is that independent?
It's like a robust recovery of compressed sensing. That's the kind of result that suggested, I guess. Not
Right. Or
usually like compressed sensing results.
No, I don't really know how that is influenced or not influenced by the kind of noise though. Like I'm not sure how much, I really don't know. Like I don't know how many assumptions on the kind of noise you have to make, because this one especially, like, it's adversarial noise. So they're really trying to get, what's the worst case scenario of noise you can find. So it should be the exact bound if the bound was general enough, but I don't know. They present some similar example, but in 2D. I'm also slightly confused about this. So it's a pretty similar scenario. They just try to recover some digits from the news data set rather than some 1D signals. And they have some weird artifacts happening in the TV case, and they just say because the images are treated as vectorized 1D signals. But then they also claim earlier in the paper that when you have an image, then the TV is computed in the kind of like 2-dimensional sense. So looking at the derivatives of both like X and Y components, I'm not completely sure of why this is happening. But they again, it's like a similar setting in which they just like plotting the different noise levels across the, if you move on the horizontal line and then on the vertical. So if you go down the vertical lines, you see different reconstruction methods, and these are just error plots. So they just plot the reconstruction minus the original one, and they just like basically look at this, how these things look like. And again, I think there's nothing too surprising here. The iterative networks seem to be performing better, and if you pump up the noise too much at some point, it just doesn't work that well. And similarly to earlier, you can see some other error plots against the relative noise level. Same, like, I'm not sure if there's anything here that was not expected, but yeah, it does seem like in these specific scenarios, the neural networks seem to be robust, or as robust as TV is for this particular case. So an interesting thing to note is that what they use as pseudo inverse here is like a very particular choice, or whatever, like a double dagger is a very particular choice. So they somehow using some sort of like Tikhonov smoothing norm, which seems reasonable because there are smooth solutions. But again, it looks like a very particular, very specific choice for these examples. And what they claim, yes, is that the neural networks are robust as TV. And again, I'm always just wondering, like seeing the examples we've seen, is L2 a good measure for this robustness? Is that because, like, again, we're talking about something very specific. We're talking about can we perturb the data so we get can we perturb the measurements so we get some screwed up data? So what does screwing up mean in this particular case? Like if you're thinking about robustness in the sense of neural networks, so we're really wanting to try to find some sort of adversarial attack, then probably this adversarial problem will be some like small quirky thing, maybe, I don't know. And another thing that I am particularly interested about is instead of like trying to think about things being robust to some noise, which it's a pretty ill-defined thing, I would say. Like there's no like exact in this paper, or like there's no definition of what robust means. Can we talk about robustness or regularization properties in a kind of like one-to-one way? Like, can we say this is robust because it's actually regularizing a problem that was ill-posed, or this is robust because it doesn't cause more ill-posedness in something that was already not ill-posed? Well, I don't know. I think there's some things that should be clarified. And another thing I want to think about, or I thought it was an interesting question, is like how can we characterize this regularization or this robustness? We're clearly changing slightly the problem we're solving by adopting a neural network, especially when we try to, or when we start doing all these choices of what do we use as a pseudo inference? What are we inputting here? What are our regularization parameters? Like all these parameters are changing the problem that we had at the beginning. So maybe the problem that we're solving now is actually not ill-posed. So what does robustness mean here? It's like my algorithms don't explode when we're trying to solve an inverse problem that has been already regularized. So maybe it's not an ill-posed problem anymore. Or we're saying that, no, wait, like this neural network is actually really good because they inherently solve the ill-posedness of my problem. Again, I think those are interesting questions that, you know, taking even these examples, we could like try to explore which bit is solved by which component of my problem. More examples. They have an MRI example. This is synthetic data. I think this one is quite cool actually, because you can see the whole setting is very similar to the previous setting. So in the top row, you can see the TV reconstruction. So you start with a noiseless one, and you can, I don't know, you can see it probably, yes. Like here, you just have a nice example where there's like some sharp edges with different colors. And as you start attacking these with some adversarial noise, things start getting blurry. So basically, it looks like, you know, especially the boundaries between different colors have been perturbed in a way that when you try to well, they kind of like in the reconstruction, they just get, I would say blurry, maybe that's the wrong word, but like they get messy. So there's like some sort of artifacts appearing really on the edges of these like big figures, mainly.
So they still vectorize the image and then apply one to it?
What, sorry?
They still vectorize the image and then apply TV to the vectorized image of the vector?
I think they apply the 2D version of that because they explain that on the paper, and I think it's not super clear in the experiment. But also looking at the results, I really think that it's like the two, like the discretized two-dimensional version of the discrete operator. But again, like one really cool thing of these images is that they show what is an adversarial attack for an ill-posed problem. So if we have TV, what's the worst noise that we can add? I mean, it doesn't show what the noise looks like, which is sad because I would like to see it, but it shows you what kind of problems it kind of translates to in the reconstruction. So it really looks like when you're using TV, what is very, very sensitive for you is the boundaries. So you have to do something on your measurement so your boundaries get problematic. Like that's what I'm taking. Like again, that's a personal opinion, but that's what I'm taking from this plot. And then if you look at the networks, and again here they're just comparing with an iterative unroll scheme, and they use the same relative error, but for adversarial noise, which is, you know, specific to this network. They actually find some really funny things, or I think very interesting things. So what the network, like what the noise is doing, is basically just creating artifacts, like on purpose, like directly. It's like, oh, what's the best way of fooling someone to believe there's a tumor, or just add a tumor in the measurements, which is quite smart, but also tells us something more about what the nature of the neural networks is and which kind of regularization they are imposing in the solution, and what are their like kind of like weak points, if you want. And one of the claims they do, because, you know, in this case, you could say like, all right, you're telling me that the neural networks are more stable, but then you're showing me these plots. And to be honest, if you had to like look at these things in a kind of like medical setting, I know these things look sharper, but I'd rather a doctor seeing something that has some blurry edges than something that has some like funky, like little, I don't know, weird things that were not at all in the original image, right? So it's a bit like shooting at your own foot. Like they say that neural networks are more robust, but then they also in the images, you can see that the kind of perturbations that are found on the data, like on the output, can be like quite problematic. And then they kind of solve this by saying, actually, this is not a problem of the network, it's really just the adversarial noise. if you look at the same adversarial noise that we applied to the neural network problem, but we apply it to TV. So we try to solve using TV, but with the corrupted measurements that were corrupted specifically to fool your neural network, you still get some pretty bad weird artifacts here. So again, they kind of like justifying it by saying it's not a problem of the solver, it's still a problem of, I would say it's a problem of the way we measure the distance between outputs, because it is true that we obtain more error by performing some weird modifications in your measurements that affect the contours of your plots in a TV reconstruction setting. But again, like if you compare it with L2, but there is something that has the same noise level, which could produce something that would be much more poisonous to us, even if the noise, even if the reconstruction error is actually smaller than the one that you've created by generating problems on the boundaries. So again, I think all these things boil down to, you know, what does robustness mean? How are we measuring this? What are these adversarial attacks protecting us against? Well, more of these plots. You see a similar performance. They're being really good at like claiming a point and be very consistent throughout the whole paper, which is like super lovely to read, because then you can just like really follow and say like, okay, for this case scenario, it also works. This case scenario, it also works. And again, they claim that in this particular case, neural networks can also be as robust as TV. They show these very interesting adversarial attacks I explained. And in this case, they say that fully learned approach are not much better. And I think in this particular case, they're just using, you know, the same same operator for their forward, their inverse problem. So it kind of makes sense that you cannot learn something that is much better in this particular case, especially when you split it up really in your network, right? Like it's not that you're like combining them in some fancy way. You just have a concatenation of like a learned inverse operator and then some like learned kind of like tiramisu net that makes your inversion kind of nicer in a way. So if you split it up, then it kind of makes sense that you're learning something that is more or less as good as the actual one. So I think in this case, it would be much better to add some really like if you really break the inverse crime, like maybe this fully learned approaches would be better or more interesting. Another case, similar case scenario. Now we use CT, we show another example, and you can see like pretty much the same things. So for TV, boundaries are sensitive points. For neural networks, artifacts are a more sensitive point, which again is a good thing, right? Because now we're saying if we use an adversarial attack for these networks, it's creating something that we are actually afraid of. So probably it means that these neural networks are already characterizing quite well, even if it's just by you know, like the enemies of my enemies are my enemies. I'm not sure that applies, but like the idea that if you attack this guy, you get something that I'm really afraid of. You know, probably this guy thinks in a similar way than I do. So I think this is actually quite relevant and very interesting. And again, this is just same thing that they did before. Just basically saying that this difference between these two is the way that the adversarial attack is being created, not just the way we find a solution of this problem. So what if we mix them up and we use the adversarial attack that's been created for the neural network, but we solve the problem using TV, and then you also get some incredibly quirky stuff. In this case, they don't have the other errors because they're quite expensive. But again, the conclusions are similar. Like I really like that it just like goes across a bunch of different examples, and like it kind of finds the same kind of underlying like problems and results. Yes.
Could you go to the previous?
Yeah.
So, I'm just wondering if with TV, to solve the problem in TV subject to
Yeah.
constraints.
Yeah, they don't act. Yeah, here they actually use so they add the constraint on the minimization. So they add it with like a localization parameter. So it's the unconstrained
Well,
version.
then it's not really comparable. Yeah. Because if you
That
did
is true.
that, what they claimed in the beginning, then the image in the lower right corner would have a very high TV with a small oscillation. And this would be very expensive given the same constraint. So I would probably they just keep the same regulation parameter for everything.
Yeah, that's true.
Sorry,
Yeah. I think it really depends on the way you. I think it really depends the way you choose the localization parameter on the unconstrained TV localization. So if you choose it carefully, I mean, I know it's not exactly the same because before you were constraining by the noise level, now you have to choose a new localization parameter, but you can find an equivalent formulation. I think they do. I mean, they do it with a grid search, so you could say that maybe they don't have enough. Maybe they find it empirically, so I'm not sure how close this. So let me think. So they do have the amount of noise, right? So I think they do try to find the good localization parameter, which would correspond to that. And then they pretend, then they kind of forget that they had. They use a lot of things like the best for this, but I mean, like, so when they explain how they choose these parameters, they say like, we've chosen the optimal for this case and things like that. So I'm not completely sure because this sometimes it doesn't explain exactly which optimal with respect to what. Like, I would personally not be too worried about this because I think, you know, it's a matter of constants after all. Like, I think the trends would be quite similar. You mean like, I mean, it is true that this, and I mean, like, you know, it could be not completely consistent about like, is this a 2% noise and here it is as well? That's what I mean, right?
I assume that they have the same bound on the noise for
Yep.
TV and the network. But then they use the same regulation parameters for.
I'm not.
So they, and if you want to choose the regulation parameter such that the solution of the problem with such that this matches a noise level, and this outcome would depend not only on the noise level, but on the particular instance of your data.
Yes.
So the regulation parameter in the lower
should depend on the data.
Or it should be different from the value in the upper right.
Yes, yeah, but I think it might be like a. If you look at the, oh, you mean, yeah, this should have like a. I can't remember. I can't remember. I should look at it. But I know it's adapted. I know it's adapted. So I would expect them to be different. But again, like, I mean, I think the key fact here, rather than, you know, the actual numbers and like the actual number of regression parameter, I think what is quite interesting is that the difference between the kind of noises and the kind of like effect it does are like slight difference.
I'm not convinced that the conclusion that if you have the same noise you have this with the data and then use TV in the correction, and also you will get that noise results in that. Because that's
As
very
this one.
expensive for TV. You might get also product, but that's very
Yeah.
expensive for TV, so you shouldn't get this with TV.
Okay, I know what I mean now. Yeah, you might be right. You might be right. Yeah, we should look at it more carefully. I had not understood you.
My-
You mean like you're talking about this specific image? Okay, okay.
and
So,
the
yeah,
other one is
yeah, 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 yeah. I cannot remember the
What
other
it
one.
would have done, perhaps, is,
This one is, yeah, this one is not too bad though, right? Because like in the rest of the image it is quite conserved. So
Sure, but it has oscillations, and oscillations are
Yeah.
very expensive.
yeah, but I mean, again, like if you have like very strong oscillation in your measurement, like you can try to, like it's probably already smoothed out a bit, but it's probably like quite hard to completely get rid of it.
But
It is true that for this one, it really doesn't hold on.
The strain formulation of T, you just say, okay, I have that much noise. And if you have small oscillations, but many of them.
Yep.
In the data, then you just
The big, yeah,
just find them out.
yeah, yeah, yeah. Yeah, I know.
So what I think is happening perhaps is that they use the same representation parameter in the upper right and in the
Yeah.
lower right corner, which is wrong.
Yeah.
For comparison purposes.
Yeah.
And if they did it the way they claimed in the beginning, with the constraint formulation, then they would have different images.
Yeah. Yeah. No, that's a really good point. Yeah, we can look at it. I don't want to say they do or they don't because I don't remember and it's not my paper. So, but yeah.
Sure.
Yeah, that's a good point. We should check. Right. They also try in some real MRI data and they basically see some, sorry, I'm just spitting through because it's almost the time, right? Similar comments, and that they do a couple of like general comments about robustness and neural networks, and one of them is thinking that training without noise is really equivalent to doing some sort of inverse crime. In my understanding, an inverse crime is something slightly different because they say like, oh, doing this training with noise later is like an inverse crime. So what we're going to do is just change our model to have noise on it. So basically we're training with the noise already, which again, I think is slightly different to what at least in my experience I had seen as inverse crime. Like inverse crime was more like a validation thing in which you should not test your data in something when you already know your problem. Like if you can go back and then change your model to add that, then I mean, isn't that the actual inverse crime then? Like when you already the two things are matching. So I would say the way I was reading about it and I was understanding the way they were posing this problem, I think it sounded a bit more like some sort of like out of distribution problem, where if you're training on noiseless data and then you're trying to measure against something that has noise on it, then you're like trying to recover something that it was not in the distribution, or that might be far in some way from the distribution you trade on. And maybe that, oh, there's a question in the chat. Okay, I'll address that. Maybe I can address that later. So yeah, I mean, that's just my question. And then last thing they say is like, okay, we think that neural networks are actually robust for inverse problems, so that's not a problem. But we want to maybe use that for something. No. Sorry. So they say, well, what if we use that for something else? Like they want to classify on top of something that's been solved or some like the solution of an inverse problem. So basically they'll have some sort of like, first we reconstruct a solution and then we classify it. And basically they say, and they find adversarial noise against that classification instead of the reconstruction, and basically say that it's still not robust. Like if we use first neural network to reconstruct your solution and then you classify it on top, you still have all the same problems because the problems come from the idea of classification rather than the fact that you're using a neural network. And they show some plots. I don't have time to go into the details, but it's a classical stuff. Like we have some reconstructions that basically look like nines, but some of them are actually classified as something else because we attacked in a very particular way. So again, this work analyzes the robustness of deep learning-based solution methods for inverse problems. I think it's very interesting to try to separate These problems are ill-posed, okay? So they are not robust in general. So I would like to really be able to debate or separate if this fact that they are being robust in a way, or that we're regularizing, comes from the training in the neural networks, from the architecture of the neural networks, or from the model that we're attaching on it. So a lot of those neural networks have some model-based approach, kind of like fused in the middle, like what are the losses we're using? Are we actually putting more information than the one we think in our models? Another question I had is like, okay, the adversarial noise doesn't seem to be as bad in an inverse problem scenario. And my question is like, well, is it not that bad because like normal noise is already awful? Like, is it that we cannot find an adversarial noise, or is that like really pretty much all noise, if we don't regularize our inverse problem, is already an adversarial attack? And again, the same thing about like inverse crime and jittering. I think jittering is very interesting and it makes a lot of sense, but the way I understand it, I think in my head, it kind of makes more sense as some sort of like solving an out of distribution problem rather than an inverse crime. But I'm not an expert on machine learning, so my mind can be changed. And this paper gives some really nice empirical proofs. It shows, I think it's really good, it's really cool. And I think it was quite useful for me, because when I think about robustness, I think about a completely different thing. So I think, in my case, trying to prove robustness, or trying to prove robustness for an inverse problems was a completely different task. But maybe it is easier, or maybe there is a new area of work trying to prove robustness in some of these sense here, like, is the training robust in some way, is the algorithm stable with some conditions, or other proofs that already tackle this kind of, like, I don't know, new perspective on robustness for inverse problems, or is this a new area? I don't know about it, and it would be really cool to think about it. And sorry, I took more time than the one I was allocated to.
So, are there questions?
Are there any questions? I don't think they can hear you.
Yeah, I can write chapter also. But are there questions in the audience to start with?
So you touched on it, but you're saying there's nothing about how dependent it is on this initial choice of a double dagger, like the regular, they just choose one and go with that
Yep.
the whole time. Okay.
Well, I mean, it depends on the different settings, but they do choose
but
one.
for each problem.
Yeah. And I think it'd be interesting to see, compare with more detail what. Oh, sorry, maybe there's something else.
No, it's me.
Okay, sorry. So yeah, I mean, anyway, if there's someone online, they ask about the choice of the first kind of like approximated inverse of A, and they do take a specific choice for each of the problems, which is already starting with something that is a bit regularized, and then you kind of like polishing your image. And I think it'd be quite interesting to do some more studies on how much are we regularizing on that step, and then just making the image better. So we're like already solving the inverse problem, or the problem with the inverse, the instability of the inverse problem with the first step, and then just enhancing your image in some way. Or no, maybe we're actually not doing that much on the first step, and then we're actually doing an amazing job with our neural network. And I think it'd be interesting to do some more studies on the difference between them. Yeah. Or even looking at proofs, like, are these problems actually opposed, like the ones we're solving in the neural networks? Because it could be that neural networks were not robust for well-posed problems. Like, that could also be the case, and it seems that at least if we have regularized the problem, the neural network is not adding instabilities, which is already a really good result.
Any other question?
Or comments?
Question or comments online? Well, it seems there are no more questions, right?